Welcome back. We are now moving forward to section 3.2 of your textbook. It begins back on page 254. Take your eyes to the sketches for the polynomial functions. Again, polynomial functions are going to be continuous functions. Not only are they continuous, but you can't even pick up your pencil. So this is like the Harold and the Purple Crayon that we talk about oftentimes. You'll notice that there are functions in figure 3.6 that are continuous, but we have to pick up our pencil, and therefore they would not be considered polynomials. Also in 3.7, you'll see one that has a sharp turn. It looks like our absolute value function. It's a function, yes it is, but it's not considered a polynomial function. Today we're going to extend our discussion beyond quadratic to what we call higher degree. N equals 3, 4, 5, 6. We are really limitless when we talk about higher degree polynomials. And they have several characteristics. Now you know that our goal here is ultimately to sketch by hand. We were talking about that in section 3.1. I know that we like to have our calculators close at hand, and we always like to have them to verify our work. But again, we're wise mathematicians. We're using the information that we have before us, the analysis that we can create on our own using algebraic techniques, so that we can do some additional point plotting, connect the dots, and have a smooth curve. In this section, I've broken it down into 3 homework assignments, 3 separate assignments, 25th today, 26th tomorrow, and then ultimately the 27th. And you'll notice here, we have few problems to do, but the directions are sketched by hand. So we will have to use the information that we're gathering along the way in order to do exactly that. You notice that we talked about that quadratic function yesterday, and we knew that it turned into the parabola. We've been studying that for some time now. We've also talked a lot about the cubic function, and we said that that's an increasing function across the entire domain, but it slows down near the origin, and it sort of kind of looks like an S shape. Well, we notice here that this is what we would call an even degree. And this is what we would call an odd degree. Other even degrees are 4, 6, 8, 10, and so forth. Other odd degrees would be 5, 7, 9, 11, and whatnot. We also noticed with the quadratic that the lead coefficient was extremely important, that A value. And we said if A was greater than 0, opens up. And we said if A was less than 0, opens down. Well, in algebra, we have actually something that's called the lead coefficient test. And this is quite honestly the very first thing that you're going to want to do before sketching by hand. And there's some rules that go with the lead coefficient test. So let's take a look over on page 256. This is a box that you really want to memorize to know what to do or what to anticipate ultimately or beyond the zeros. So this lead coefficient says it's like my Buzz Lightyear problem, to infinity and beyond. We have the Cartesian system, and here you are standing at the origin as if you're looking at the board. This is your right hand, and if you're looking this way, you're looking towards positive infinity. And this is your left hand, and if you were looking in this direction, this would be towards negative infinity, and of course this is the x-axis. So the question that we have is, as x approaches infinity, what in the world is f of x doing? Is it getting larger? Is it getting smaller? And then we say, as x approaches negative infinity, what is f of x doing? Is it getting larger or is it getting smaller? Well, this as x approaches positive infinity, we call this the right-hand behavior. And as x is approaching negative infinity, we call that the left-hand behavior. And so we have some rules. in the lead coefficient test. And it goes like this. If n is even and a is greater than 0, we say rises left, rises right. I want you to think about that parent function. N is even. Think about f of x equaling x squared. It's the easiest one to think about. When we have a positive lead coefficient, we are rising left and rising right. If, on the other hand, if n is even and a is less than 0, then we say falls left, falls right. In other words, we've taken this parabola, and now we have f of x equals really -1 times x squared. Well, you know when there's a -1 seated directly in front of the variable, this is a reflection with respect to x-axis. So we fall to the left, and we fall to the right. On the other hand, if n is odd, I want you to think of f of x equaling x cubed, the cubic function that we first talked about today. If n is odd and a is greater than 0, then it's going to look exactly like we've drawn. So again, if I'm standing here at the origin and I look to the left, we say falls left, and I look to the right, rises right. But if n is odd and a is negative, again, it is as if we've taken that cubic function and we've multiplied it by -1. We've now reflected it with respect to the x-axis. Now our picture looks like this. And if again I'm standing at the origin, I'm going to say this one rises left, falls right. This is our lead coefficient test. This helps us to anticipate what this curve is going to do, again, before we ever put pencil to the paper. Example 3, you can take a look at it. There can be subsequent terms, there can be linear terms, constant terms, which for graphing purposes are important. But in the final analysis, once this curve heads towards the infinities, the lead coefficient test will tell us where the points are going to finally show up and not change direction anymore. So lead coefficient test, very, very powerful. Page 256, please review it. Please learn this. You're going to have to know it. Over on page 258 again, we've talked about zeros. We've unpacked this over and over and over again. I really like the box that's highlighted in yellow on page 258. Take a look at it. It defines, again, solutions, zeros, x-intercepts. We've said that a zero or a solution is the x value that corresponds to the equation f of x equals 0. If the zero is real, it is also an x-intercept. If the algebraic zero is complex, then it's not going to correspond to an x-intercept. Now, I want to give you a few facts on top of this information. We're going to talk about existence, and then we're going to talk about characteristics called multiplicity. So, again, extracting from the text, you may want to kind of align yourselves in your notes to be thinking about it this way. First of all, the existence of zeros. Are they there at all? And how do we know? So the existence of zeros. And to summarize, it says this. If n equals the degree of the polynomial, then n equals the maximum number of zeros in, now be careful with this, this will make your eyebrows go up, in the set of complex numbers. So pump the brakes for just a second. Be reminded that if this is the set of complex, that all real numbers are also considered complex. All real numbers are considered complex. So when we talk about n being the maximum number of zeros, they could be all real, they could all be complex, or they could be some combination of the two. So numerically, we need to get an understanding of what that means for the existence of these zeros, because we need to know what we're looking for, okay? So here's something to think about. If n is even, if the degree of the polynomial is even, then the zeros will exist this way. F of x has n real zeros, or n minus 2, or n minus 4, all the way down to no real zeros at all. If n is odd, then f of x has n real zeros, or n minus 2, or n minus 4 real zeros, all the way down to 1. If n is odd, expect 1 real zero at a minimum. And the reason that we say that is that complex zeros, be reminded, complex zeros exist in conjugate pairs. So this is where the multiples of 2 are coming from. So from an expectation standpoint, you can decide whether I'm looking for an x-intercept or not, and how many of them I may or may not find. So for example, let us take a look at the checkpoint for example number 4. Let's take a look at the checkpoint for example number 4. It says f of x equals x cubed plus x squared minus 6x. Well, again, f of x equals 0. When I'm looking for zeros, this time I'm going to factor out the GCF of x, which is going to leave me x squared plus x minus 6. I'm going to further factor this as x plus 3 and x minus 2. Zero product property says that each of these will be equal to 0 potentially in order for the product to be equal to 0. X equals negative 3, x minus 2, x equals 2. So in this case, all the zeros were real. I have 3 x-intercepts in my graph at 0, 0, at negative 3, 0, and at 2, 0. Sometimes, however, things don't work out quite the way that we anticipate, so it is entirely possible that we could have a combination, again, of real zeros and complex zeros. Let's take a look at example number 6. This one is a little bit more complicated. Example number 6 says f of x equals x to the 5th minus 2x to the 4th plus x cubed minus 2x squared. In this case, again, GCF x squared leaves me x cubed minus 2x squared plus x minus 2. Looking further then, I can group within these GCF again. This is going to leave me x squared times x minus 2 plus 1 times x minus 2. X squared, x minus 2, and x squared plus 1. Now, if I set each of these equal to 0, notice what happens with this last one. This is a squared, so we would call this a double root. We have to have 5 zeros, but 2 of them are here. But that's still an x-intercept. One of them is here, and the other 2 are complex. So here's a scenario where we have a combination of real zeros and complex zeros. If you push ahead with me in your textbook, page 262, I'd like for you to take a look at the home assignment, number 9 through 22. This is a matching exercise again with the higher degree polynomials, trying to anticipate what these are going to look like based upon the lead coefficient test, the number of intercepts that we can be looking for. Continuing on, 17 through 22, again, sketching, looking at transformations, this time with respect to the cubic function, as well as 29 through 36, lead coefficient test. Tell me what's happening, left hand and right hand behavior, and 37 through 48, using finding the zeros algebraically. So expect to have to factor here, guys. Expect to have to factor to find your zeros. At this point, I'm going to stop the video because I think that you have enough that you can handle that first assignment.